Okay, everyone, welcome back to class. It is the 8th of October. We're right on schedule with everything. We've begun chapter 4 last Thursday, and so we're making progress here with our chapter on quantitative data. Got the first part of the project graded and back, so you can see your grades and your commented your graded project 1 on Canvas. If you didn't get 100% on that and you'd like to improve your grade, you can resubmit. So just look at my comments and fix whatever is missing or incorrect there. Resubmit and I will regrade it. If you don't understand what you got wrong, then email me or we can meet in Zoom and talk about that. So, but overall, very good work on that. And the first part is sort of the foundational part because you get your data set that you'll use for the rest of the course. So if you get that data set right on part 1, you really can, go forward with the rest of the project. So I think everybody's got good data there. So let's see what's coming up here. Next Thursday we'll have next Thursday we'll have fall break. So that's coming up, and then a couple weeks after that, we'll have exam 3. So exam 3, it's still a few weeks out, about 3 weeks out. So that's kind of nice. Exam 3 will cover just chapter 4. Do you guys have anything you want to ask me? Any questions you want to go over? Anything you're struggling with? So let's just remind ourselves a little bit about the structure here of the class. There's pretty much 2 kinds of data. There's the categorical, often called qualitative data, and then we also have quantitative. Okay, so in chapters 2 and 3, we talk about categorical data pretty much exclusively. There's a little quantitative in there, but most of it's categorical. And we also use chapters 2 and 3 to introduce statistical inference, so confidence intervals and hypothesis tests. Right, so we learn about the graphics, the statistics, the tables, and then we do confidence intervals and hypothesis testing for categorical data. Chapter 4 is where we start thinking about quantitative data, and we're basically doing all of the same things with this different kind of data. We're looking at tables, we're looking at graphs, we're looking at statistics, and soon enough, we'll do confidence intervals and hypothesis testing. So it's very much, there's much in chapter 4 that parallels chapter 3, and that's good. It's kind of nice to have, 2 topics that are similar in a lot of ways. So, but they are different in that we have a different kind of data, right? So that's where we were at. I believe on Thursday we were talking about, we introduced 3 or 4 different kinds of graphics, and then we were looking at new statistics. So we looked at the mean, the mode, right? And so yeah, that's basically where we're at, is looking at these new numerical summaries of quantitative data. So we got to the median, and the median basically means middle, right? So in the Latin, that would be the middle, and that's exactly what it means in stats. It's the measure that splits the data set in half. So it truly is the center of the data set. Okay, so so how do we find it? Well, you take the data and you put it in order. You put it in order from smallest to largest, and then you get the data value that is right in the middle, if there is one. Okay, so what do I mean? Well, let's look at this data set here. Okay, so small data set. Sometimes it's nice to have small data sets to demonstrate the mechanics of something, right? So if you're going to find that median, you take that data set and you put it in order, and then the 3 is right there in the middle. That's the median. Okay, and so it's especially easy when you have an odd number in the data set. So here n is 5 and 5 is odd, and so when you have an odd data set, then the median is a value in the data set. It's right there in the middle, 3. Okay. If you have, let's say we add 1 to this data set. Let's say there's actually a 7 there. Then that would mean that we have 1, 2, 3, 4, 5, 6 values, right? So that would be an even number. When n is even, it's a little more work, but it's hardly, very difficult. So what we'll do is the same thing. We'll put the data in order. Okay, so 2, 3, 3, 4, 6, and 7. But notice there's no number in the middle. Okay, so there's 3 and 4. There's 2 numbers in the middle. So what do we do with those? We're going to take the average of those 2. So we take the average of the 2 middle values. So 3 plus 4 divided by 2, that's 7 divided by 2, that's 3.5. Okay, so 3.5 is not a value in the original data set. Okay, so that happens when you have an even number in your data set. So again, we take the data, put them in order, and then if there's an odd number in the data set, then we simply just grab the number in the middle. If there's an even number of points in the data set, then we take the average of the middle two. So pretty easy, right? Okay, so what are the advantages? Well, it's easy to compute. It's one advantage. And it's not affected by outliers very much. That's considered an advantage of the median over the mean, okay? It's best for skewed data because it is resistant to outliers. So we like statistics to be resistant to skew and outliers. There are a couple of disadvantages to the median. It's less universally understood. Okay, so if you were to, pick a random person from the population, it's very likely they would understand the average or the mean. But the median, it's not quite as well understood. So, if you pick, if I had to guess, if you pick a random person out of the population and ask them to compute the median, they might not be able to do that. Okay, it's just not as commonly used, so it's less universally understood. And then, so when you're communicating results, it's not, you're not really, it's clear. It's not really clear if the median is a better number to use. So anyway, that's just considered, that's a disadvantage of the median. The other thing is that it's hard to use in theoretical results. And the reason why is because there's no formula for it. Do you see any formula over here for the median? Not really. We see a series of steps. So you can program a computer to find the median. All a computer needs is steps, but there's not really a formula you can use. And formulas are so important for building up more and more complex ideas, right? So that's considered a disadvantage of the median, that there is no formula for it. Okay. So let me demonstrate this idea of resistance a little bit more. I think we talked about an example neighborhood last time. So let's say you live in a neighborhood. It's a very small neighborhood, so we can do the math fast. There are 3 houses there, and each house is worth $300,000. Okay, so obviously the average for that neighborhood, the mean would be 300,000. Okay, so the mean would be 300,000. What about the median? Well, it would be the same thing, right? It would just be that number in the middle. So the median would be 300,000. Okay, so the mean and the median are the same sometimes. But I think we had the example of, having an eccentric billionaire moving into your neighborhood, and maybe you've got like a really good view, and they build a $30 million mansion in that neighborhood, right? Okay, so what happens to the median here? Well, the median is going to be the average of the middle 2 numbers. So the median is actually unchanged. The median is still $300,000. The median didn't change at all because of that outlier. And that's considered good because this neighborhood, if you think about like a typical house in this neighborhood, it really is like a $300,000 kind of house, right? Most of the houses there are $300,000. That $30 million house is the outlier, right? It's just, it's kind of unusual, right? So, but what happens to the mean with that $30 million house, right? So we have 300,000 We have 3 of those, so I'm going to go times 3, and then we're going to add in the $300 million, the $30 million house. That's just sort of an outlier. We divide by 4, and now the mean is over $7 million, right? So does that make sense? So, the mean is basically destroyed by that outlier. Okay, $7 million does not really capture the typical middle value for this data set anymore. Okay, and we discussed that last time, right? We said the mean is sensitive to outliers, whereas the median holds, right? The median actually didn't change at all because of that outlier, and that's considered a strength of the median. And so if you work in fields like real estate, or if you're an economist and you're studying incomes, then typically they'll use median income and median house price over mean because it's less resistant, because the median is resistant. Okay, so that's a good thing. So we know how to calculate it by hand. It's actually very easy. You just put it in order and you pull the data out. Let's talk about how to use software for this. So go ahead and fire up GeoGebra, and I'll show you how to find all of these common statistics very quickly with software. And so we have an example data set here where we've asked 10 college students, how many hours per week do you work outside of the home? Okay, so the college has a group called the Data Science Group, and so they're basically statisticians and data analysts, and they track all sorts of information about students because it helps us do a better job at the college. And I can tell you for sure that the number of hours that students are working, besides school, really it can have an effect on students. So we want to have an idea of how much time students are working. Do they have full-time jobs? Do they have part-time jobs? Are they not working at all? It's important for us to understand these kinds of things. And so that's what this data set is getting at. Okay, so for example, this student here has a full-time job. They're working 40 hours a week. This student here has a part-time job. They're only working 5 hours a week. This student here is, well, this student here is kind of like a half-time, right? Working half-time, right? So this makes sense. There's all sorts of different scenarios out there for people, different situations. We want to find the mean and the median for number of hours worked for students. Okay, so we have a sample of size 10, and this is definitely quantitative data, right? The number of hours you work is a count of the number of hours you work, right? So it's quantitative, so it's chapter 4 stuff, and we're thinking about mu for the whole population. That would be the average number of hours worked for all students at the college. X bar, this would be the average for our sample, okay? So let's go over to GeoGebra and give this a try. So sometimes you have to click around a little bit until you get the toggle button to pop up. Then we hit the 3 dots, and we need to get the data into GeoGebra. Okay, so if you can cut and paste or copy and paste data, that's smart, and you should do that. This data set's pretty small, and the PDF document is, for some reason, it's kind of difficult to copy and paste values from it. So I'm just going to type it in. But when you get data sets that have 30, 40, 200 observations, you don't want to type that in by hand, right? So hopefully you know what I'm talking about with copying and pasting. When you get into the homework and these data sets are larger, try copying and pasting the data directly into GeoGebra if you can. Okay. So we have the data there in the spreadsheet. We need to tell GeoGebra what data we want to work with. I get lots of emails with asking this right here. Students will forget to highlight the data. They'll come over here, they'll do their one variable analysis, they'll hit their sigma x, and nothing will appear. And it's because we haven't selected anything. Okay, so you really do need to select the data, otherwise GeoGebra doesn't know what to use. Okay, so the first step is we select the data, then we hit this histogram looking symbol over here, and then we're going to go to one variable analysis. You can only have one number for the number of hours you work in a week, right? So, if you work 20 hours this week, then you didn't work 24 or something, right? So it's one variable, and so we hit that, and then to get the mean and median, we're going to come over here to where it says sigma x. Sigma appears in so many different formulas in stats that it's just sort of our way of saying, hey, here are the common statistics. So we hit the sigma x, and there we go. It calculates the mean and the median very quickly for us. Okay, so they're right there, mean and median. So the mean is 23 and the median is 26. Okay, so the mean in this case is x bar because it's a sample, and that value is 23. The median is 26, right? Or did I do that backwards? No, that's right. Okay, all right. So then we want to create a graph of the data using GeoGebra. And at various times in the project, there's still part 2, 3, and 4 to do. So, every now and then you'll have a graph to create. I recommend using GeoGebra for that. You can use Excel or Google Sheets or anything you want, but GeoGebra is designed by educators, and it really is pretty easy to use. So anyway, to create a graph in GeoGebra, we're going to go over back to GeoGebra, and then we already actually opened it up, right? So just to remind you, we go one variable analysis, and then it gives us this drop-down menu. Okay, so I believe last time we were talking about the histogram, and the histogram is probably the most common graph to use for quantitative data. And there we go. Okay, so what kind of shape is this, and does it line up with what the mean and the median are telling us? Okay, so I would say that this is a slightly left skewed graph, right? We have one peak in the middle, and then we have a tail on the right and a tail on the left. The tail on the left is longer than the tail on the right. So this is a left skewed data set, which means we have a higher number of students down at the left end of the distribution. And what does that do to the mean and the median? Okay, so we see that it's left skewed, and the mean, which is 23, is less than the median. We know that the mean is more sensitive to outliers and to skewed values, so it makes a lot of sense that the mean would be pulled further down than the median, right? So these 2 or 3 students, it's really these 2 here. The rest of the students are, kind of working either half-time or full-time jobs, but these 2 down here, they're pretty lucky, perhaps because they don't have to work and go to school at the same time, and more time to focus on studies. These 2 lower values here are really pulling the mean and the median further down. But we saw as with the housing values, right? The mean is more sensitive. So the mean is going to get pulled further to the left than the median. So we see this a lot. When the graph is left skewed, the mean tends to be less than the median. All right. Any questions there about the median? Okay, so once you have the median in place, then we can very quickly get to the box plot. So I mentioned the box plot as a desirable graph last time. It's a nice graph for quantitative data. It does all sorts of things for us. But before we can really understand that graph, we have to know the median. Well, we know the median now, so we're ready to get going with the box plot. So to understand the box plot, you need the median because the box plot has 5 different numbers. Okay, so the 5-number summary, it's summarized in a box plot. It consists of the minimum and the maximum. So those are easy enough. It's just the smallest value and the largest value. Then the other 3, there's 5 numbers here. The other 3 are the first quartile, the median, and the third quartile. So we're solid on the median, but what are these quartiles? Okay. Well, think about percentiles. There's basically 100 percentiles, right? There's the first percentile, the second percentile, the third percentile. There's, so 100 is too many really for us typically to think about. Um, so when we're considering the population, there's certain percentiles that are a little bit easier to work with, and those are the quartiles. Okay, so what the quartiles do, they basically break up the data set into 4 equal pieces. Okay, so the first quartile is the 25th percentile. The median actually is the second quartile. We call it the median, but you can refer to it as the second quartile. The third quartile is the 75th percentile. Okay, so that's what the 5-number summary is. It's the minimum, it's the maximum, and then the middle quartiles. Okay, all right, so the rest of this, we could, talk about all these words, but it's just not going to make a lot of sense until we've practiced with the quartiles. So let me skip over these for a little bit, and we'll jump right into an example, and then we'll come back to those words and definitions when we need them. Okay, so in this data set, we're looking at number of items produced per hour. Okay, so we're kind of back to the idea of quality control and just sort of control in general. If you're, say, if you own a factory or a plant, right, and you're building lots and lots of things, you need some way of monitoring how things are going at your plant or factory, right? So very common to do that, to take just sort of basic summary statistics and understand, how various parts of the plant or the factory are operating. Okay, and so one way of seeing how the operation is going is by counting the number of items produced per hour, right? That's not the only thing you care about, but it's an important part. So every hour, or maybe you have a sample of hours throughout the week, you simply, whoops. You take like a random sample of hours, and then in those hours you count the number of items that are produced. Okay, so for example, in this randomly selected hour there were 24 items produced. Okay, and later on you have another randomly selected hour, there were 20 items produced. Then in this hour there were 7 items produced. Okay, so things vary from time to time, and so there's some variation there. And we want to get an idea of how that variation works, right? So first of all, we're going to find the quartiles. So this diagram is really nice for understanding the quartiles. Okay, so we have the min value, we have the max value. The median is in the middle, of course. The median splits the data in half. So we have 50% below, and we have 50% of the data above. If it's the middle value, that's what it has to do, right? So we have roughly 50 below and 50 above. And while 100%, 100 different percentiles, that's so many different little pieces that it's hard to use that sometimes. What we do is we have 4, okay, different places that we consider, right? And it helps us, having 4 different parts to the data set, that's easier for us to understand. So what are those 4 parts? Well, we have Q1. Okay, so we start at the min, and by the time we get to the 25th percentile, we have 25% of the population below that value. Okay, so we call that a quarter, right? And since it's the first or the lowest quarter, we call it the first quartile. And to make that a little bit faster and easier to write, we just call it Q1. Okay, so it is the same, it's equivalent to the 25th percentile. So that is the 25th percentile. They're one and the same thing. Okay, but Q1, first quartile, is just a little bit easier to use. Okay, so, but that's only the first quarter, right? There's more data there. So we keep going through the ordered data, and eventually we get through another 25%. So that's the second quarter, right? So by the time you're done with the second quarter, you are now at the 50th percentile. and that's more or less equivalent to the median, right? And you can call it Q2, the second quartile. These are all, pretty much interchangeable terms here. Median, 50th percentile, Q2. So that's the second quartile. Then we keep going, right? There's still more data ahead, right? So we're going through the ordered list. Eventually, we get through another quarter of the data. At this point, we have 3/4 of the data behind us, right below us. So this is the 75th percentile. Okay, so it is identically equal to the 75th percentile. But we'll typically call that Q3, or the third quartile. Okay. Then there's still more to go, right? We still have another quarter left. If 75% is below, there's still roughly 25% above. And could we call that Q4, or the fourth quartile? Yeah, I suppose you could. I've never actually heard it called that. Everybody just calls it the max at that point, right? You're at the max value. Okay, so these are the 5 numbers. And these having these 4 divisions in there, these 5 numbers actually are, it's easy enough for us to make sense of it, right? Just 5 different pieces. It usually produces a pretty nice segmentation for us. So that's why we like these 5 numbers. It's not like 100 different percentiles. It's just 5, and it turns out to be pretty useful for us. So how do we find these quartiles? How do we find the first quartile? Well, it turns out that we need to find the median first. Okay, so that's the first thing we do to find our 5 numbers. Okay, so we're going to arrange the data in ascending order. Okay, so from left to right, we're going to put the data in order. Okay, so can't skip this step. So just go ahead and do this along with me. So I'm just taking our data set here and putting it in order. Okay. So we get it in order, then we find the median. And that's also, as I pointed out, called Q2. So how many do we have in this data set? There's 2, 4, 6, 8, 10, 12, 13 items here. Okay, so 13 is odd, and that makes it a little bit easier. We know that it's going to be the middle value here, right? So when you have 13 numbers, that means you have 6 on the left, 6 on the right, and 1 in the middle. So I'm going to go 1, 2, 3, 4, 5, 6 in from the left, and then I'm going to go 1, 2, 3, 4, 5, 6 in from the right. And then so that means there's a number in the middle. This is the median, also called Q2, the second quartile. Okay. So from there, the easy way to think about this is to realize that basically cuts the data into 2 halves, right? We have the lower half, and then we have the upper half. Okay. So if we're looking at this lower half here, if we forget this upper half for a second, notice that Q1 is the middle of the lower half. So Q1 is itself like a median, right? It's a median for the lower half of the data. So all we need to do to find Q1 is find the median of this lower half of the data. Okay, so we have 6 in the lower half. 6 is even, so we know we're going to be taking the average of the middle 2. Stop me if you have any questions here. So I'm going to go 20 plus 22 divided by 2, and we have our first quartile there. Okay, so Q1 is the median of the lower half of the data, and Q3 is the median of the upper half of the data. And then, so yeah, Q3, if we only consider the upper half of the data, if we ignore the lower half for a second, Q3 is the middle of the upper half. So Q3 itself is like a median, but a median only for the upper half of the data set, right? Okay, so it's back to finding medians again. So there's 6 in the top half, and 6 is even, so we're going to take the average of the middle two. So 27 plus 29 divided by 2, 28. Okay, so why do we care? Well, it gives us a nice segmentation for the data set. Okay, it tells us the middle of the data set. So, if I'm looking at this and I have to tell you what an average number of parts produced per hour is, what's kind of a typical production like for this factory or this plant, I would say about 26 items per hour. And that's what the median tells us. Okay, but there are days that, there are hours that have fewer items produced, right? So about 25% of the hours there are going to have 21 or fewer items produced. And I know that about 25% or higher will have more than 28 items produced. So it gives me an idea of the spread, it gives me an idea of the center, and we've already talked about why we care about these things, right? Spread is basically telling us consistency, okay? And definitely for like a factory or for a processing plant, consistency is almost always desirable, right? So it gives us a way of quantifying those things. All right, but we can do more with it, actually. We can even determine the shape of the distribution sometimes. Let me show you. Okay, so we're going to compute the distance between Q1 and the median. Okay, so Q1 is here, the median is here. What is that distance between those two? So it's like a spread, but a spread on the left end of the distribution. Okay, well, it's easy to compute. The median is 26, Q1 is 21, so that distance is 5. If we do the same for the right end, we're looking at the difference between Q3 and the median. So Q3 is here, the median is here. So that distance, again, is like a spread for the upper half of the distribution. So Q3, we calculated that to be 28. So 28 minus 1 is 7. Sorry, it should be a 26 there. It's Q3 minus the median is 26, so that's 2. So it's asking us if it's skewed. How can we determine that? Well, think about what those two numbers are telling us. They're telling us that this distance here is more than twice this distance here. So if we were to imagine a histogram, wouldn't this side be more spread out than this side? So it might look something like that if we were to draw a histogram. Yeah, because again, this distance here is twice this distance here. So it's a little bit more compact on the right and a little bit more spread out on the left, which to me indicates that it's probably left skewed. Okay, so those 5 numbers are, useful for all sorts of things. We know where the center is, we have an idea of the spread, and we're even able to make a conjecture about skew here in the data. Okay, so what is that 5-number summary? Well, it's Q1, Q2, median, Q3. Okay, so 21, 26, 28. Then 2 more numbers, the min and the max. Okay, and that's 7 and 30. Okay, and these 5 numbers alone, which are not, none of them is too hard to understand, I think. These 5 numbers alone can tell us a lot about a data set. Okay, let's keep going. We can go further here with the 5-number summary and actually get a way of determining and defining outliers. Okay, so it's asking us here in this data set, are there any outliers? Well, what is an outlier? An outlier is a value that sort of stands alone. It's a value that's definitely unusual and probably indicates that there was something going on there that was just fundamentally different than the other values in the data set. Maybe not fundamentally different, but probably, right? So let's look up here at the data, and you guys tell me, are there any values in here that seem to just not belong? Or are they all just kind of in line with each other? Is there anyone that just sort of stands apart? What do you guys think? It's in order. Any values here that just seem totally different? Yeah, the 7. Yeah, if there is one that's different, it's got to be the 7, right? The rest of these pretty much are close together. 15 is a little bit weird too, maybe. But 7, there's just, it looks like there's something different about 7. Or maybe not, right? Who knows, right? When you don't have a definition for outlier, it's a bit subjective. So what we're going to do now is actually get a definition for outliers. And that's progress, right? We'd like to have a way of defining what an outlier is. And so there is a definition for an outlier. It's basically anything that falls outside of the fences. Also, what's a fence? Okay. So like I was saying, stats has all of these quirky names and words. So what we're going to do here is talk about the fences. The fences help us define what an outlier is. Okay, so basically what we're going to do is we're going to look at our data set. Okay, we're going to start at Q1, and we're going to say, okay, Q1 is a small value. It's not terribly small. It's the 25th percentile. And we're going to go a further distance down from Q1. Okay, then we're going to go up to Q3, which is a large value, not extremely large, but you know, it's the 75th percentile. And we're going to go just a little bit further than that. In fact, the same distance we went down here. And what that creates are the fences. We have a lower fence and we have an upper fence. It's an interval. If you fall in that interval, you are not an outlier. You might be a small value, you might be a large value, you might be very large, you might be very small, but you're not an outlier if you're within those fences. Now, if you fall outside of those fences, then yes, you are an outlier. Okay, you are extremely tall, you're extremely short, you're extremely wealthy, something is just fundamentally different about your situation, okay? So what's the formula for these fences? Okay, it's here on the formula card. Okay, so we have a left fence and a lower fence and an upper fence. So the lower fence starts at Q1 and it goes 1.5 IQRs to the left. The upper fence starts at Q3 and then it goes the same distance, 1.5 IQRs to the right. What on earth is an IQR? The IQR is the interquartile range, and it itself is a measure of spread in the data. It's the 75th percentile minus the 25th percentile, right? So inter means between the quartiles, and it's a range. So it's the Q3 value minus Q1, and it basically tells us the distance between the 25th percentile and the 75th percentile. So it is a measure of spread in the data. And we like having measures of spread because spread is related to consistency, right? Okay, so let's calculate IQR. So that's Q3 minus Q1. So Q3 is 28, Q1 is 21. So 7 is that spread between Q1 and Q3. So we have a measure of spread here, and we like that. Okay, so that distance there separating the 25th percentile and the 75th percentile for this data set is 7 items. So it's telling us how spread out it is. Then we can take that along with the fence formulas, and we can determine if we do have any outliers. Instead of, you know, arguing and not really getting anywhere when it comes to outliers about that 7, right? What's the status of 7 here? We can actually, you know, all agree if it's an outlier or not. Okay, so with the lower fence, it's going to be a lower value Q1 minus 1.5 IQRs. Okay, so Q1 is 21, and we're going to go minus 1.5 IQR. The IQR has been calculated to be 7. Okay, so it's calculator work. We're going to go 21 minus 1.5 times 7, 10.5. Okay, so this lower fence here is 10.5. The upper fence starts at a higher value in the data, Q3, the 75th percentile, and then it goes out the same distance, but to the right. So by the time you get out to this upper fence, you are pretty much, kind of at an extreme value for the data set. So what is Q3? That's 28 plus 1.5 times 7. And we can do that on the calculator as well. That's 38.5. So the upper fence here is 38.5. Okay, so what does that give us? It gives us an interval of values. If your value is in that interval, it can still be large, it can still be small, it can be very large or very small, but it's not an outlier. It's not fundamentally different from the rest of the data. If you're outside of that interval, though, probably something fundamentally different is going on there. So do we have an outlier? Where is 30? 30 is about right there. That's still in that interval of kind of, non-outlier values. What about 7? Where does 7 fall, guys? Do you see how 7 is falling outside of the fences? Okay. 7 is an outlier. So you were right to think that that's our outlier. Okay. And now you can, we've got, the definition of outlier there of the fences to back us up here. 7 is less than 10.5. So it's an outlier. So what happened? Maybe they were having some problems with the machines. They had to shut down, the production run for a while, recalibrate. Maybe somebody forgot to show up for their shift, right? There's all sorts of different reasons why. But probably something during that hour changed or was different at the factory. And maybe you need to investigate it, or maybe it's just kind of okay, right? But it is something to consider. Great. So we have everything we need now. We have a way of defining outliers. We have the fences. We have the 5 numbers. We're actually ready now to pick up a new graphic, this thing called the box plot. Okay, and you'll see these if you look for them, especially if you're doing work that involves, quantitative data. If you end up doing any investing, if you're already an investor or in the future you do some investing, like in say a 401k or something, and you look at stocks like shares in companies, they'll often use the box plot to communicate ideas about center and volatility in stocks. Okay, for example, there's a million uses for box plots, but that's one that you'll see if you know where to look for it. Okay, so how do we draw the box plot? Well, we start by drawing the box part of the box plot first. So the box part is Q1, Q2, Q3. Okay, so no matter what happens with the box plot, you can always get that part right. So we're going to go right to 21, and we're going to draw a line right above 21, a vertical line above 21. That's the first part of the box for the box plot. Then we're going to go to 26, which is Q2, and we're going to put the same thing above 26, another vertical bar, about the same, well, the exact same height if we can, if we're drawing it by hand. Then we go to Q3, which is 28. Okay, so with those in place, we'll then put a horizontal line on top and a horizontal line on bottom. That's the box part of the box plot. And that graphic alone tells us useful information. It tells us what the median is, right? It's saying your typical hour, you're going to produce about 26 items. But, it could, it does go as high as 28 as at the 75th percentile and, down to 21 for the 25th percentile. So, very typical values would be between 21 and 28. Okay, that's the kind of information we can gain here. And what do we see about skew? Do you see how this part is more spread out? There's more spread here than here. So they both have a quarter of the data. So that indicates that it's denser here than over here. Well, if it's denser, then it means it's got a shorter tail on that side, right? So again, just like we said above, we're starting to get this picture in our minds, right? It's a little bit more spread out on the right. I'm sorry, a little bit more spread out on the left than it is on the right, right? So it's just denser there on the right than on the left. So we're kind of getting the idea of a left skewed distribution. But that's only the beginning of the box plot. At this point, we're going to identify the outlier. And like we were saying, we need to set this apart. Okay, we're not going to throw it out of the data set, but we need to indicate to people and to ourselves that something weird probably happened at that time. Okay. And so the way we indicate that is with an asterisk. So any outlier will be indicated with an asterisk. And some data sets will have multiple outliers. You can have you can have 0 outliers, you can have 1, you can have 2. In theory, you can have any number of outliers. Okay, but 2, 3, 4, these are kind of typical for homework and exams. Then what? Well, the full name of the box plot is box and whisker plot. So I know it's just kind of quirky, but so what are the whiskers? The whiskers are lines that come out of the ends of the box. Okay, so what they indicate are values that are large and small, but not outliers. We indicate outliers with asterisks. So what the whiskers do, or they tell us how far up and down the data go before they become outlier. They tell us how far non-outliers go, both above and below. So what am I talking about? Let me show you. What I'm going to do for the upper whiskers, I'm going to find the largest number that's not an outlier. Okay, so if we look at this data set, the largest number that's not an outlier is 30. Okay, 30 is still within the fence, right? So what I'm going to do off to the right is I'm going to have a line that goes out to 30. And there's a fair amount of difference. There's a fair amount of different styles for the box plot that you'll see from one software package to the other. Once you understand one box plot, then the others will make sense. But some software packages will leave it like this. Others, including GeoGebra, will put a little line at the end like that. So let's just stick with the GeoGebra convention there. So there is our upper whisker. And what it does is it says, okay, the real data, the actual values in our data set go up as high as 30. Okay, so the non-outliers go up to as high as 30. So it's giving us another measure of spread. Okay, then on the left, we're gonna have another whisker, and this one's gonna go down to the smallest value that's not an outlier. Okay, so this will lose you a point on the exam. It's really tempting to do this. So some students will just automatically draw that down there, and they will immediately lose a point. Okay, the outlier is intentionally isolated from the rest of the data. Okay, we want to point that out. We want to isolate it so we can think about it and maybe do some follow-up on it. And so what the whisker does is it will not go to any outlier. It will not go to the outliers. Okay, it will go to the largest value, the smallest value in this case that's not an outlier, and that's 15. Okay, 15 is the smallest value that's not an outlier. So I'm going to have a line that goes down to 15. Okay, so again, you want to imagine a line that starts at the left end of the box, and it's going to go down to 15. Now, some software packages will leave it like that. Others, including GeoGebra, others like GeoGebra will have a little vertical bar. Okay, so every software package does these slightly differently, but once you understand, the box plot, then all of the other shapes will make sense very quickly for you. Okay, so there we go. There's our box plot. And it sort of does everything all at once. It tells us the center, 26. It tells us the spread, right? So 21 to 28 is where the middle, 50% of the data are, right? So between 21 and 28, you're getting half of your hours. Then between 15 and 30, you're getting, pretty much the full range of non-outliers. And then we do have an outlier down here. So it's really quite a useful graphic. And I hope you can just look at that and kind of imagine a histogram, right? We have the bottom half of the data, the bottom 50% is spread out over these values. The upper half is spread out over there. So I think you can tell it's just more concentrated on the right and more spread out on the left. So if we were to imagine a histogram here, you're looking at like half of the data in here and then another half down here. So it would be quite more spread out there on the left, on the right. So that is looking like a left skewed distribution. So the box plot, it just does everything. Very useful graphic. Okay. Let me show you how to do this on GeoGebra. Any questions there about that? So again, I just can't emphasize, well, a couple things I want to point out. Make sure the whisker never goes down to the outlier. That's impossible. Okay, so if you're on the exam and you see that, then you've made a mistake. Okay. The other thing I really just I don't want to use strong language, but I just hate this so much when I see the box plot on the number line. Okay, I see this a lot, and it's just it just sets my teeth on edge. Okay, so hate to be so negative, but please don't do that. Okay, please don't. It's just a big mess, right? So please make sure your box plots are separated from the number line, that they're standing above, separated from the number line. You can do box plots vertically. So if you imagine the whole thing vertically, that's fine, but just don't ever put the box plot on the number line. Okay, good. All right. So how do we do this in software? So if you're actually doing analysis for a company or for a scientific study, you're not going to have a paper where you publish things, drawn by hand, right? You do this in software. So let's see how to do this in GeoGebra. Okay, so let's kind of refresh this. So we hit the toggle, the three dots. We need to get the data into the spreadsheet. And, like I was saying before, if you can copy and paste the data into GeoGebra, great. And usually the software for the homework will allow for that. So I'm just gonna, but PDFs, it's kind of hard to cut and paste sometimes with PDF. So I'm just gonna type in this data here. Okay, so this is the data set, same data set, and I'm gonna type it into GeoGebra here. So go ahead and, if you can, go ahead and do that along with me. If it's too awkward in Zoom, then just watch. There we go. So just like before, we need to highlight the data. All right. Once we've done that, we'll hit the histogram here. This is one variable analysis because, in a given hour, you can only produce so many parts, right? You can produce 20 items, but you can't produce 20 and 26, right? So we're going to hit one variable analysis, and there we go. There's our histogram. Sure enough, it's left skewed. The box plot is also here. So we go to the drop down and we select box plot, and there we go. That's the same one we drew by hand. It just looks better because it's software, but it's the same thing, right? We see our outlier. They use an X instead of an asterisk there, but same thing. So we have a 7 there, and then the lower whisker going to 15, the upper whisker going to 30, median at 26, Q3 28, Q1 21. So it's the same exact graph, just looks better, right? I can't remember if it's part 3 or part 4 of the project. Or maybe part 2. I wish I checked before class. But on one of those parts of the project, you'll be working with quantitative data, and I highly recommend for that part of the project to use the box plot. So you can do it right here in GeoGebra. Then you get your snipping tool. You grab it like this, and then you copy and paste. You come over to your Word document where you're putting together your project, right? And you just paste it in there. So it looks really nice, okay? Or you can export as a picture, like a JPEG or a PNG file, whatever you prefer there. Okay, so that's how we do it by hand and with software. Are there any questions there about the box plot? Okay, so let's look at a few different common things, common styles for box plots. And we want to be able to use a box plot to determine the shape of a distribution if we can. So these are some kind of common box plots you'll see. So this first one, notice that the median is right in between Q1 and Q3. And the left tail or whisker is basically the same or very close to the length of the right whisker. If that's the case, I think you can imagine that this would be a symmetric kind of distribution, right? So if the median is roughly at the center of the box, it's rarely right at the center, but more or less if it's at the center and the whiskers are of equal length, then it's probably a symmetric distribution. Now, if the median is closer to Q3 than it is to Q1, that means it's denser here, right? You have 25% of the data there, and another 25% there, right? So it's pretty dense on the right. On the left, it's a little bit more spread out, right? Or a lot more spread out. So that would mean we have left skew, right? So we can imagine this would be a left skew distribution. So on the exam, you'll probably get asked this. I'll show you a box plot, and I'll say, hey, is this a left skewed, a right skewed, or a symmetric distribution? Okay. What would right skewed look like? Well, if it's right skewed, that means typically that the median is closer to Q1 than it is to Q3. And typically the left whisker will be shorter than the right whisker. Right? This is roughly 50% of the data here spread out in that distance. On the left, the lower half is spread out by about this much, right? So you can just tell it's denser here and it's more spread out over here, which would indicate kind of a right skewed pattern. So so basically something like this, right? It's pretty tight on the left and then a little bit more spread out there on the right. That's kind of a right skewed pattern. And then of course, just to really hammer this down, if you have an outlier, then the whisker will not go to that outlier. Okay, so make sure you have a space in there. And notice, yeah, instead of an asterisk or an X, they use an open dot. Like I was saying, every software package just seems to do things slightly differently, but it's just a superficial difference. That the rest of it is, the calculations are all the same. Okay. Any questions there? Okay, so a lot of students, well, not a lot, but occasionally I will get students that try to add in the fence to the box plot. Don't do this Okay, you can draw the fence at first to determine your outliers, but it's not really necessary to do that, right? You can just look at the fences and determine if you have outliers. Okay, so please don't include the fences. Um, it's just not how we do box plots. Okay, we use the lower fence and the upper fence to determine if we have outliers, and so we will calculate the fences. But when we have our final box plot picture, we do not include the fences. Please don't put them in. Okay, so that's what it'll look like at the end. Okay, so there we go. All right, so yeah, we're making great progress here with the box plots, and just progress in general. Let's see, it's the 8th. So yeah, we're moving along here. We're not going too fast. We have about 20 minutes left. Does anybody want to talk about the box plot a little bit more? Anything that you're not clear on there? Well, let's continue on then. Let's actually go back to an idea that we've discussed before, this idea of resistance. Resistance means that extreme observations have little effect on their value. So think of the housing example, right? So that really, kind of wild house there, $30 million house, it didn't change the median at all. The median went from 300,000 to 300,000. But the mean was just totally wrecked by that, right? It went from 300,000 up to 7 million. And so we want to consider that idea of resistance. Okay, the median is resistant. That's one of the reasons we like it. Okay, um, so let's think about our measures, these measures that we've been developing. Okay, so we have measures for center. Okay, so we have the median and the mode. These are resistant. Okay, so we have a resistant measure for the center. We have a resistant measure for the center. So median and mode are two common ways of measuring center. They're both resistant. What's the other way of measuring center? The mean. Okay, it is not resistant. Okay, now we still use it all the time, probably even more than the median, but it's not resistant. So if you have outliers, then you'll probably want to switch over to the median. If you have skew, you probably want to switch over to the median. And again, if you work in fields like real estate or income, if you're an economist and you're studying things like income distributions, it's very common to talk about median values instead of mean values. It just gets a better idea of typical kind of middle of the distribution. So those are measures of center. Okay, so measures of center, it's the 3 M's: mean, median, mode, the 3 M's. Okay, those are easy enough. What about spread or variability? Okay, how do we measure variability? Well, we talked about the IQR, right? It's a measure of spread. Spread, variability, same thing, right? Similar idea. So there we go. We picked that up, right? It's that distance between Q1 and Q3, so the inter between quartiles range, so the distance there between Q1 and Q3. It's a measure of variability, and it's a difference between two medians. So if it's coming from medians, then it itself is also resistant. So if you're trying to understand spread in a data set, and that data set has outliers or skew, then we'll tend to use the IQR. It's a great measure of variability. Okay, what other measures of variability do we have? We have the range. Okay, the range is simply max minus min. And you can imagine that that's highly variable, right? It's highly non-resistant to outliers, right? The range is max minus min, so if you have any outliers, then those are actually going to make up the formula for the range, right? So the range is definitely not resistant at all. So it's a big weakness of the range. Then we have our old friend, the standard deviation. More on this later, but I just want to point out that the standard deviation is not resistant either. So if you're trying to measure spread with a data set and the data set doesn't have outliers or a lot of skew, then the standard deviation is typically what we'll do. I'm going to skip over the variance for right now. We'll come back to that. Okay, so I want you to be really, really, really comfortable with this graphic. I'm going to ask you on the next exam questions related to this. Okay, so what is it? It's thinking about skew and resistance at the same time. So what are our 3 or 4 different kinds of shapes? We have the bell-shaped curve, which is symmetric. We have left skewed, we have right skewed, and we briefly mentioned the uniform. Let's ignore the uniform for right now. So in a symmetric distribution, we have one peak in the middle, we have a tail on the left, we have a tail on the right, and the two tails are roughly the same. So when it's perfectly symmetric, I think your intuition will just, you'll just kind of agree with me here that the mean and the median are going to be roughly equal. In fact, perfectly exactly equal if it's perfectly symmetric. So if it's perfectly symmetric, then there's no skew. And if you had to choose the best measure of center, you'd probably say the mean. Because if there's no skew, then there's not really any resistance issues, right? So the median would still work, but we all know that there's going to be a lot of people out there that don't really know what the median is, unfortunately. So we'd probably stick with the mean in that case. How would we measure variability? Same kind of thing. If there's no skew, then we'll go with our old friend, the standard deviation, right? That distance from center to inflection point. IQR is fine, but yeah, I mean, probably most of you guys hadn't heard of IQR before class today, right? Or before this semester. It's just not as commonly used as standard deviation. Okay, so left skew. So if we imagine pulling on the left end of the distribution, then it goes longer on the left, shorter on the right. So what happens to our mean and our median? Okay, well, okay, so kind of look at my hands here. If you have a symmetric distribution and the mean and the median are at the same value, then the mean and the median, are on top of each other, right? But if you introduce some left skew, then what happens? Well, the mean and the median start to get pulled to the right, but the mean, being more sensitive to the outliers and the skew, will get pulled further to the left than the median, right? So in that case, the mean would be less than the median. Okay, and I hate to scroll around. I know it's not a lot of fun to watch scrolling around on these things, but isn't that what we saw up here? Remember this example? We saw left skew, and we saw that the mean was less than the median. So we've already seen this. Okay, we're just kind of formalizing it and summarizing it in this table here. Okay, so if you have left skew, then the mean is probably less than the median, and vice versa. If you have a mean that's quite a bit lower than the median, then you probably have some left skew. So if there's skew, then you probably don't want to use the mean because it's going to be affected by those outliers. Okay, you want to choose a statistic that's more resistant. You'd probably want to go with the median. And what about for measuring variability? Well, we have our old friend, the standard deviation, but it's super sensitive to outliers and to skew. So we would probably want to go with this IQR for measuring variability. Yeah, it's less familiar, and your readers are probably going to have to look it up to try to understand what it is, at least some of the readers, but at least it works, right? It's not going to be as sensitive to those outliers. Okay, what if we have right skew? So if we have right skew, then you can imagine the distribution gets kind of pulled to the right. Now, so if you have mean and median in a symmetric distribution, let's see here, something in the chat. On these graphics, would the mean still be centered? That's a great question. The mean will be pulled a little bit away from the peak. So what is the peak? The peak is the mode. Yeah, we don't talk about the mode as much, but the mode will always be the peak. But yeah, if there's left skew, then if this is the mode, then the mean will have to be pulled to the left, and the median will also be pulled to the left, but not quite as far. So the mean will not appear under the peak anymore. It'll get pulled to the left. Does that make sense, Noah? It's a good question. Good. All right. Thank you for asking. So right skew, the mode stays put. The mode is still under the peak, but the mean and the median are going to be on the move, right? But which one moves further? Well, the mean is more sensitive. So let's see. Hopefully I get the direction right for the camera. It should be going further to the right than the median, right? So that means the mean will be more than the median, probably. So if there's skew, then we're going to avoid the mean and the standard deviation. We'll go with the the median for measuring center, and we'll go with the IQR for measuring variability. Okay, so let's do some more with GeoGebra and really try to understand resistance here. No questions? Okay, let's return to that data set with the students that are working. And we already used this data set, I think, right? So we did the mean, we did the median, and I believe I showed you the box plot. But if I didn't, we've already done a couple box plots. So actually, let's just go ahead and do this again. It's super easy in GeoGebra. So so here's our data set, and we're going to pull this into GeoGebra. So for GeoGebra to work, I'm going to just reset everything here. So we'll hit the toggle, the 3 dots, spreadsheet. And we'll put the data in. Okay, so there we go. Then to get the box plot and the statistics, we need to highlight the data. Okay, once we've highlighted the data, we come back over here to where we see the histogram. It's one variable analysis. This is number of hours worked, remember? And so we have the histogram, but we're thinking more about the box plot right now. So we'll go over to the box plot. Okay, so there are no outliers. So even that person who's not working at all is not an outlier. Okay, and the person working 40 hours a week is not an outlier. So there we go. There's our box plot. Then to get well, before we calculate mean and median, well, we can see them right there. But if we look at that box plot, what would you guys say? Is that a left skewed or a right skewed or a symmetric distribution? Would you guys say right skewed, left skewed, or symmetric here?
Left.
Oh, great, left. Yeah, 50% roughly is in here, and then the upper 50% is roughly in here. So it's denser on the right than on the left. So it's more spread out on the left, which would indicate a left skewed graph, right? So we have a left skewed graph. Not heavily, but yeah, I mean, and then we see Q2, the median is closer to Q3 than it is Q1, right? So yeah, it's left skewed, and that's what we're seeing with the mean and the median, right? So we hit the sigma x, and again we see median is 26, the mean is 23, and that's exactly what we'd expect. Okay. Let's see here. Good. All right. Which one would be better? Probably the median. So I would say the median is a better measure because of the skew, the left skew. Okay. You know, there are some students that aren't working at all, but you know, almost all of these students are working at least like a half-time kind of job, right? So you know, 26 to me just sounds like it captures the middle of the distribution a little bit better. Okay, so yeah, so left skewed graph this agrees with mean less than median. Okay. All right. So you guys try one. I want you to look at this data set here. This was a few years back now. It was in-state tuition for pretty much not everyone, but most of the colleges and universities that operate in Utah, mostly that are mostly based in Utah, except for a couple of these like the University of Phoenix. I don't know why we didn't have Western governors in here, but anyway, it's a pretty comprehensive list of higher ed institutions in Utah. And so each one of these will have a tuition, an in-state tuition. I want you to find the mean, find the median, and create the box plot here for this data set. Okay, and you don't need to do it by hand. I want you to use the software here. Okay, so I'll go quiet. We don't have a lot of time here. We've only got 4 more minutes, but just give you a couple minutes here to get going with this and at least try this out. Okay, and then we'll come back together and work on it together. Okay, did anybody get the mean or the median yet for this? I know we don't have a ton of time here, but with software, it doesn't take too long to do this. So let's see here. Armand's got it. Those are both correct. Good. Thank you, Armand. That's perfect. Very nice. Okay, so let's see how to do that. So we put the data into column A, then we highlight it. And then for tuition, it's a one variable kind of data, right? Because you can't have $2,000 and $4,000 for your tuition for your in-state, right? So there we go. And the histogram definitely is indicating right skew. We wanted to do the box plot here, so we'll go to the box plot, and yeah, sure enough, it's pretty tightly, it's pretty dense down here in the lower end and more spread out on the upper end. And I think last time I told you that that's very common with money because it's hard for a college to be less than $0, right? So if the average is about 6,000, then yeah, certainly you can go all the way down to 0. You can make your college free. Um, but there's only a distance of about 6,000 there at the bottom. But are there colleges that are 12,000? Sure. Are there colleges that are 18,000? Yeah, I mean, there's colleges that cost like 50 or 60,000 a year. So it just kind of keeps going and going off to the right, and we get a right skewed. And then if you'll give me one more minute here, so the mean is 9448.8. The median is 6248. Sure enough, the mean is more than the median. And that's what we said would happen typically if we have right skew. The mean will get pulled further to the right than the median. Okay, so great. We have to end there. We're out of time. Are there any questions that you want to ask before we sign off for today? We're pretty much right where we need to be. Go ahead and have a look at your first part of the project. Make sure. I think everybody had good data for the first part. So that's really the key part for getting the whole project right, is getting that data right. So that's good. And then I'm still working on the exams. I hope to have those by Thursday, but certainly by Friday I'll have those graded. So if there's nothing left, if there's no questions left, I'm going to go ahead and sign off. You guys have a great day, and I'll see you back here on Thursday.
Thank you.
Thank you.